Now in this movie, we're going to start with this essentially data from a stove diagram and look at the stability of different layers. And it assumes that you know about the dry adiabatic lapse rate and the saturated lapse rate. So we're going to write down the temperature. We're going to start. Let's say I want to know the stability of kind of each of these layers. Okay, and so I'm gonna write down the parcel temperature, and I'm going to start in let's say the surface, so 34 degrees. The dew point itself. So look at the parcel dew point. Starts off at 22, and we're going to take this parcel and bring it up to the next level. The parcel, because it is unsaturated, cools at 10 degrees per kilometer, or 5 degrees each of these steps. So it's going to cool to 29 degrees, as we saw before. The dew point itself also changes, and that's going to be important in one of the layers that we look at. And its lapse rate is 2 degrees every kilometer. So each of these half kilometer steps is going to cool by 1 degree. So I'm going to get 21 degrees here. So we're still unsaturated, so we're fine. But now what we do to kind of address stability is we compare the parcel temperature at that level that we've now pushed up with the surrounding air that it's at. And so what's happened is we've pushed this air up. Now it's 29 degrees. The surrounding air is 36 degrees. It's colder than the environment. And so what's going to happen is this parcel is going to sink back down. So if I push it up, it comes back down. This is very much like the bowl with the marble at the bottom of it, where if I push it up, the marble comes down. And so we would say that at this layer, this is stable. Okay, so now we're going to do we'll do the next layer. Okay, and I'm going to just move over to just this is just to make it clear. There's no difference in parcel dew point. Okay, so parcel temperature, parcel dew point, but I'm going to start at the half kilometer level, and since I've already written stuff in the half kilometer level, I will I just write it over on this side. So we start off with 36 degrees for the parcel and 29 degree dew point. We force it up one level. This brings this down to 31 degrees, and the dew point goes down to 28 degrees. So we're still dry, we're still unsaturated, and so on. And notice what happens. Just from a stability point of view, I take the parcel temperature, I compare it with the environmental temperature at that level. I notice that it is warmer, the parcel temperature is warmer than that, and so this parcel will keep going up. So what happened is if I took this air and that starts off at the same temperature as its surroundings, I force it up, it's now warmer than its surroundings, it's going to keep going up. And this is what would be called unstable. All right, and we can see that stability also if we do things like let's look at the saturated level at 1.5. So I'm going to skip a level just to show an example. We start off at that level at 25 degrees, a dew point of 25 degrees. We're going to take that parcel, push it up to the next level. It's going to cool at the saturated rate, which means it's only going to cool by 3 degrees. That gets me 22 degrees and a 22 degree dew point. The dew point follows the thing. Now, for stability, I then compare that new temperature with the air that's around it. It's warmer than the air around it, so it would keep going up. So this would be considered unstable, because if I push it in one direction, it keeps going in that direction. And we can do this for all of the different levels that we would like to do. So that is we can determine the stability for any of these layers in this way, and just just write the and then just label each of the each of these levels for like stable or unstable, or stable or unstable.